So welcome everybody to this presentation today from Dr. José Fernandez, who's very kindly joining us from Madrid. Just to let you know, José, it's raining here today in Brighton, UK. I hope it's a bit better in Madrid.
It's a very sunny day. You can see now. Natural light. Not...
Cool. Today's presentation is going to be on ISE and PPOOA, which Dr. Fernandez will explain to us all in more detail in a moment. But first of all, let me introduce him to you by giving you a bit of his biography. So Dr. Fernandez holds a PhD in computer science and an engineering degree in aeronautical engineering, both from the Polytechnic University of Madrid. For the last 20 years, he's been an associate professor there. The areas of interest include systems engineering, real-time systems, software engineering, and case tools. So all the things that we in the INCOSE UK MBSE working group are really interested in, so that's good. His focus today, of course, is as the methodologist for PPOOA, which is an architectural framework for real-time systems, and also for the bit we're going to hear about today, which is the integrated systems and software methodology of ISE and PPOOA. That's what we'll look at today. And his professional credentials are that he's a member of both the IEE and INCOSE, and participates in the software engineering body of knowledge and the CBOC, as we know, the systems engineering body of knowledge, and the requirements engineering working group. And he also has the honour of being involved with the PMI, the Project Management Institute, and reviews the PMBOK and the Requirements Management Practice Guide. So I'm sure you all agree, more than very well qualified to talk to us today about these subjects, of which we're all very interested in. I rattled through that because got lots of content we want to get through. I'm now going to hand over to Jose for his presentation. The format we expect it to be, will go on until about 1:45 or 10 to, so about 45 to 50 minutes. And then we'll leave a little bit of time at the end for some questions, although we may not be able to fit in all your questions. So obviously, if that's the case, we can review some offline and get back to you with anything that you might have there. Hope that's all good. I'll now, without further ado, hand over to Jose. Let me do that. I'll stop presenting. There we go. And I'll also turn my camera off so it doesn't distract you.
Thank you very much. Thank you very much, James. Thank you for inviting me to present this method. As James mentioned before, the acronym of the method, that is this one, ISE and PPOA. ISE is for Integrated Systems Engineering. So this part of the method is related with model-based systems engineering. And this part of the method, PPOA, is related with software architecting. So the method is a mix of integrating a model-based systems engineering with software architecting method and a software architecture framework. This method is the result of more than 20 years of research in methods and tools. Part of this method is described in a recent book published in the US and UK by Architect House. This is the book. In the book, the things I will explain today are in the book, and the examples also are in the book. Also, you can find more information in the OMG wiki about model-based systems engineering. In this OMG wiki, there is a website related with this method. In this website, you can find interesting publications, papers, and if you are interested in some of them, you can request it to me, because some of them are copyright protected. But anyway, you can request them to me. So you have the book and you have the website, and also PPOA have a particular website. This methodology is a requirements-driven methodology. So requirements are very important in all the phases of the architecture because requirements flow down and the architecture development are achieved at the same time, are achieved in parallel. So requirements are very important in this method. It's very important for us also to use trees, so represent hierarchies, to use flows to represent functional flows mainly, and to bridge when we have semantic gaps. I will explain it later. Also, I will explain the conceptual model or the ontology that is the foundation of this method. This method has 3 dimensions that are mission, system, and software, and has a process. So it's important because the process has outcomes for these dimensions, outcomes related with the mission of the system, outcomes related with the system per se, and outcomes related with the software subsystems or software intensive subsystems. We are thinking in mechatronic systems where we have some subsystems that are software intensive. For example, in a robotic system or on our unmanned aerial vehicle. The example I will explain here is a simple example. I will not explain the software part. In the book, you have explained the software part of a very complex robotic, collaborative robotic arm. In this case, I will explain only the electrical subsystem of this unmanned aerial vehicle that is a real aircraft developed by a small and medium enterprise here in Spain, and right now tested by the Spanish Army. What do we mean by a model-based systems engineering methodology? There is a very good document by INCOSI that was coordinated by Jeff Stefan. In this document, they define a model-based systems engineering method as a collection of related processes, methods, and tools. So we have processes, steps to produce the outcomes. We have best practices or methods, and we have tools. In the case of our methodology is tool agnostic. So we can use whatever tool that has implemented SysML and UML. So currently we are using 3 commercial tools, okay, for the methodology, for applying it. There are well-known commercial tools. So for us, the important thing in the methodology right now is the process and the methods. The processes as the way to achieve steps to obtain the main model-based outcomes, and the methods are, as a set of good best practice. Some of these best practices are traditional systems engineering, for example, N-square chart. Other are more related with model-based systems engineering. But we prefer to maintain some best practices of traditional systems engineering that we think are very good. One of them is the N-square chart. So this methodology promotes a way of thinking consistently. As professor, as a consultant, one of the things I identify in my students and in professionals is the problem of system thinking, the problem of things in abstractions. For example, identify functionalities. For example, identify quality attributes. People is good identifying physical objects, the physical architecture, but people is not so good identifying functionality. So it's very important to help them to build the functional architecture. For me, it's very important. So other methodologies are more oriented to object-oriented, and the functionality is not so important for me. The functionality of the system is the core of the system. It's crucial. It's the most important thing. The most important outcome is the functional architecture. Moreover, because the functional architecture is more stable to the change in technology. The physical architecture changes with technology. The functional architecture is permanent, is independent of the technology. This is very important issue. So, in the method, we develop in parallel the system architecture, subsystem architectures, and the requirements flow down. It's very important. One of the things more difficult for people, for my customers and students, is requirements flow down. The reason is because they don't build hierarchies. They don't build hierarchical representations of the functions on hierarchical representations of the quality attributes. Some years ago, I have a customer working in the air traffic management systems, developing air traffic management systems. They show me a document that the customer did not understand. The document was the requirements document. The requirements document has more than 1,000 pages. All the requirements from different levels mixed. So the customer is normal, has no idea how to read this document. The first thing I did with them is build hierarchies, functional hierarchies. With these functional hierarchies, they can identify the requirements at each level. This is the reason of this process. So we develop the functional architecture hierarchically and the functional allocation. With the functional allocation, we identify the logical blocks that are part of the physical architecture. At the same time, we develop the requirements for the next step that are subsystem requirements. With the subsystem requirements, we identify in the hierarchy new functions from the subsystems, and we allocate each of these functions to the blocks, the parts of each subsystem. So we identify the parts, the logical parts of each subsystem. At the same time, we specify the requirements from the components. With these requirements, we can build the specialty engineers, electrical engineers, electronic engineers, software engineers, develop the components. So it's very important that the requirements flow down and the system architecture are two processes that are intertwined. They are developed in parallel. And this is very complex. Also, for example, the chief engineer of the Boeing 787 told that one of the main difficulties for them was the requirements flow down. I think it's one of the big issues in engineering. Another best practices we also recommend is the trees, so hierarchies, as I mentioned before. We use hierarchies in different steps of the methodology, in different of the process. The use of flows to represent functional flows, as in traditional systems engineering. Very important is to represent the system responses, the system threats of functionality as functional flows. In traditional systems engineering, they use functional flow block diagrams. Here we use activity diagrams, 6ML activity diagrams. We prefer to use activity diagrams instead of sequence charts or other representations used in 6ML. We complement them in some cases with state diagrams if we need to represent states of operational modes. Also, we use what we call bridges. In some cases, we identify that semantic gaps. For example, there is a semantic gap between the non-functional requirements and the architecture. The semantic gaps is breached by the breach in this for this case is what we call the use of heuristics to breach the semantic gap between the non-functional requirements and the software or system architecture. To breach the semantic gap between the system architecture and the software architecture, we recommend a breach that is the domain model. The domain model of the software part. Based on the functionality we want to be performed by software, this functionality is converted in classes, in conceptual classes or analysis classes that they have as responsibilities these functionalities. This is how we bridge the semantic gap between the system architecture and the software architecture. So we use trees for represent hierarchically, functionality, quality models, physical decomposition of the system, and the requirements diagrams. We use flows to represent behavior, that is, functional flows, to describe system behavior, represented as XML or UML activity diagrams. We use bridges to cross over the semantic gaps. For example, the semantic gap between non-functional requirements and system refined architecture is the bridge is the heuristics. And for the semantic gap between the system architecture and the software architecture, the bridge is a UML model of the classes that will be implemented as software. This conceptual model is called the domain model. This is not new, but is used by many people in the software domain, but it's very important here as well. So we use trees to represent functional hierarchies. We use trees to represent physical hierarchies, and we use trees to represent quality attributes, for example, maintainability, reliability, and safety, and the non-functional requirements that belong to each quality attribute. This tree is called also the quality model. And in the book, you have an example of the quality model we applied to the robotic arm. It's very important also to understand the conceptual model or ontology that is the foundation of the methodology. I will explain it briefly. We have a system that has parts. Parts may be simple parts or composite. We mean a composite part, an assembly, or a subsystem. Parts interact between them and is defined by the physical interface. The system operates in an environment. This operation of interaction of the system with the environment is described by the operational context. The operational context is an aggregation of scenarios of usage of the system. These scenarios also are described by operational needs. The operational needs are needs from the point of view of the actors that participate in the scenario. These operational needs are associated with identified system capabilities. What we mean by a capability, the INCOSE UK group is very good in identifying capabilities, and these people was one of the sources I use. For me, capabilities, the ability to perform of the system to perform something. So capability is the ability to perform something. So capabilities are a set of properties. These properties may be quality attributes, for example, maintainability, reliability, etc., states of the system, physical properties, or functionalities. So capabilities are very complex because they are a set of properties that may be quality attributes, states of the system, physical properties, or functionalities of the system. Functionalities are described by functional requirements, and functional requirements are allocated to the system parts. But the difference here is that non-functional requirements are not allocated. Non-functional requirements are implemented by parts, and they are implemented by the use of heuristics. This is a very important difference that not so many methods describe them very good and describe how to help people to deal with them. Deal with non-functional requirements. To deal with non-functional requirements, the way is the use of heuristics. It's the only way I find to deal with non-functional requirements. So I collect heuristics from many sources, and in the book there is a chapter dedicated to all these heuristics. Also, some time ago, we developed a tool, use intelligent agents to help people to use heuristics. So as I mentioned earlier, PPOA is Integrated Systems Engineering, and PPOA has 3 dimensions. The dimensions are the mission dimension, where we explain how we are using the system, how we are using the aircraft, and this mission dimension is described by scenarios, operational needs, and capabilities. We have the system dimension that is described by the requirements, the functional architecture, and the physical architecture. And we have the software dimension that it is described or explained by the domain model, and a structural view of the software architecture, and a behavioral view of the software architecture. I will explain these things briefly in the following slides. Here is the method, the process, the main process, the integrated systems engineering sub-process of all the method. In this process, the first thing we identify from the interaction, the main scenarios of use of the system. Also named by some people use cases. We identify use cases. Some use cases may be sunny day use cases, but other use cases may be what they call, people call misuse cases. So, for example, the use cases related with safety issues and security issues are called misuse cases. And also in these misuse cases, we have actors. For example, we have an actor bad luck. When we identify and describe the scenarios, we identify operational needs. And from the operational needs, we identify capabilities of the system and high-level functionalities of the system. And we identify in parallel the quality attributes that are important for us. Is important for us safety or no? Is important for us security? Is important for us resiliency? We identify these quality attributes, and it's very difficult. It's one of the things more difficult in the process. After we identify high-level functionalities. For identifying high-level functionalities, we use the capabilities we have identified before, earlier, and we use the domain knowledge. For example, if we are identifying the high-level functions of an aircraft, we use, for example, the INCOSI. INCOSI has a very good document related to the functionalities of a commercial aircraft. But it's very good. So use that. So the domain knowledge is very important. So based on the scenarios and our domain knowledge, we identify high-level functions. We decompose the functions into their children subfunctions. And we represent the functional architecture. That is not so only the hierarchies. We have to represent the functional flows as well. When we have the functional architecture complete, finished, this is an iterative process, we allocate functionality to logical modules. These logical modules are groups of functions that are cohesive and with minimal coupling. For that is very interesting the use of the N-square chart. And we represent the modular architecture. After we have the logical or modular architecture, we refine this architecture taking into consideration heuristics and taking into consideration a trade-off analysis for technology issues. So we apply trade-off for technologies that for implementing a logical block with a technology, we apply trade-off analysis, and after we apply, or at the same time, we applied heuristics to meet the non-functional requirements. And after, we represent the physical architecture. So, for representing the functional architecture, as I mentioned before, it's very important for us to represent hierarchy, functional flows as activity diagrams, and the interaction between the functions using N-square charts. So we have functional hierarchies, we have functional flows when we use SysML activity diagrams, but only to represent activities. We don't represent in this diagram the items that one function sent to another function. For this representation, we use the N-square chart. So the activity diagram is less complex. Other methodologies represent this and this in the same activity diagram. So the activity diagram is cluttered with a lot of information. We prefer to represent independently the flow and the interface. And this is useful also for another purpose, that is grouping functions that are coupled. We can use here algorithms for clustering. For example, there are tools. I think the Cambridge University has one tool that is used with what they call the matrix, but the same is the method developed by the MIT. And they use these clustering techniques to cluster functions into modules that are cohesive and with minimum coupling. If somebody wants to likes to know more about N-square charts, the reference I use is a book from Derek Hitchens. It's a book about systems thinking. And in this book, Derek explains, it have a good description and explanation how to use these square charts. In my book, I also summarize that. Also, we represent each function by a text and tabular format. From this functional architecture, we work to develop grouping this functionality in modules, into modules, to represent it. That is called the modular architecture. When we have the modular architecture, we apply trade-off analysis for the technical issues and heuristics for non-functional requirements to obtain what we call the refined architecture. The refined architecture implements the logical architecture and the design heuristics to take into account non-functional requirements, for example, related with maintainability, safety, efficiency, resilience. These heuristics right now are in chapter 6 of the book. So the deliverable here is the physical hierarchy, internal block diagrams to show the interactions between the parts. Here we have a part of this type. The part is C, the type is C, capital C, and the part is C. And we have the parts and the interaction. We represent also as well the functional flows, but with partitions. In each partition, we identify the part that performs the function. These partitions are also called in the methodology in SysML and UML swim lanes. We have the swim lanes. Swim lane for the part B, the swim lane for the part C, swim lane for the part A, a swim lane for the part D. Also, we described each part by a textual format. For software-intensive subsystems, we applied PPOOA. PPOOA is an architectural framework. It is not only a process. It's a process and a vocabulary of building elements. So we extend UML profile, we extend UAML metamodel to include new modeling elements for modeling real-time systems, real-time software architectures. In the vocabulary of PPOOA, we have components and coordination mechanisms. Components are, for example, domain components, structure components, process. For process, here are a periodic process and periodic processes for implemented processes that are repeated in time in the software. And also we have coordination mechanisms. Coordination mechanisms are the mechanisms supported to the communication of processes. For example, in real-time systems, in real-time operating systems, typically semaphores, buffers, mailboxes, all these things are what we call coordination mechanisms that provides capabilities for synchronize or communicate processes, mainly processes. Here is the process to obtain the software architecture. In this process, it's very important to create the domain model. So the domain model is a class representation of the objects that implement functionalities that are to be implemented by the software. So these functionalities here at this abstraction level are called responsibilities. So the domain model is represented using a responsibilities-driven approach and using what we call CRC cards, class responsibility collaboration cards, that were invented some years ago by people working in object-oriented approaches. So after building the domain model, we can build the software architecture. And in the software architecture, we have components, software components. In this case, all of the components are processes. And we have coordination mechanisms. In this case, we are representing here stereotypes in UML, stencils in Visio for representing buffers. These ones are buffers. And this one is a semaphore that controls the access to some shared component between different processes. If you have in the PPOOA website, there are some examples of application of this software architecture vocabulary. I will explain to finish. A sample developed by a Spanish company working with, I work with them to teaching them the methodology and mentoring them to apply it. The example is an unmanned aircraft, fixed wing, used in intelligence and surveillance missions. This is the aircraft. The aircraft has 2 meters of a span, 1.2 meter of length, 90 minutes of endurance is good, 15 kilometers of link range, and a cruise speed of 60 kilometers per hour. This right now it is in test by the Spanish Army. We represent here the context diagram of this aircraft. The aircraft is named Seeker. We have the main actors that are the pilot, maintenance technician, the target, and the environmental conditions. And the environmental conditions are the weather and the landing place. With this context diagram, we identify the main use cases. The main use cases are configure the aircraft before flight, manage the flight plan, communicate with the aircraft flying, manage the landing plan when the aircraft is flying, manage payload when the aircraft is flying, estimate wind when the aircraft is flying, capture video in infrared or in visual light, calculate target position, monitor the aircraft, monitor the position of the aircraft, and monitor the status and health of the aircraft. So here, this use case is related with monitoring the aircraft position and monitoring the aircraft battery, monitoring the aircraft health. Also, when the aircraft has landed, we perform maintenance in the aircraft. With the use cases and the knowledge in the domain, we identify the main capabilities. What are the main capabilities we identify here? For example, easy aircraft configuration, guide to system verification, to have guide for verification of the system before takeoff, flight planning management, autonomous flight, send and receive communications, command the payload, send video, support wind estimation. This one is very interesting. Long endurance. This is a very complex capability because long endurance has different properties. For example, the wingspan here is 2 meters because if you have a wingspan of 2 meters, the aerodynamic drag is less. Also, we have other properties. For example, the reliability of the components. The reliability of the components is important to have long endurance, and also to have a function for health monitoring. So if you have some function for health monitoring, this function supports long endurance. So long endurance is a complex capability to be implemented as properties, functionalities, and quality attributes. Other capabilities, the range, 10 kilometers here, easy assembly, less than 5 minutes, easy to transport by a soldier, for example, safe during GPS signal outage, and low noise footprint. With these capabilities, we began to build the functions trees. This is the main functionality tree. This main functionality tree is based on these capabilities, the operational needs, and the domain knowledge. As I mentioned before, the domain knowledge is in books and in technical reports. For example, in the case of aircraft, there is a very good technical report by INCOSI of the functionality of a commercial aircraft. And also there is a very good book by Scott Jackson that is called Systems Engineering for a Commercial Aircraft. Based on this, in these sources, and adapting them, we identify the main functionalities of our aircraft. Provide communications, plan and generate control aircraft movement, distribute communications, monitor aircraft conditions, very important for health, provide aircraft movement, generate and manage electrical power, and provide payload management and commands. This is the first high-level description. For each function, we have developed its own tree. Here we have the tree for F4, distribute communications. This function has 6 children. Transmit sensor measures, transmit demanded power plant, transmit demanded actuator's position, transmit switch on-off lights, manage telemetry data, and transmit video. Here we have the children of F5, that is, generate and manage electrical power. It's very important, this distribute power children. Also is very important, the functions related with electrical protection. We have protect against reverse polarity, protect against short circuits, and protect against overvoltage. So we develop these functional hierarchies to be the more complete enough. When we have the complete enough, we can build, and we have the script of the functionalities with these templates. We can go to the functional flows. When we represent these functionalities, how they interact, only the functional flow. This is very similar at the functional flow block diagram in traditional systems engineering, but using SysML activity diagrams. We don't represent here if a function sends something to another function, or if a function receives something from another function. For that purpose, we use the n-square chart. We represent in the n-square chart in the diagonal functions at the same level. And we represent in the rows and columns, in this case using the convention inputs in columns, if this function sends to this function, the input to this function is here. So inputs in columns. The row above all the functions is the items that come from outside, and this column is the outputs to outside. So we have the items that are sent from a function to another function, and the items that the functions receive from outside, and the items that the functions send to the outside. It's very important here to see also that some functions have feedback to another's. So we have elements in the upper diagonal, in the upper area, and we have elements in the area below the diagonal. It's very important. This is also very important when we use the matrix methodologies. Domain matrix, and here is very important because this representation, that is a representation of the forests, not the trees, this representation allows us to use clustering techniques to cluster functions that are very related between them or among them. When we have the functions, also we identify the functional requirements related with each function, and mainly the functional requirements related with each function are the outputs. So we have to define as a functional requirement the output of or outputs of each function. This is a technique, a best practice I learned from people from Rockwell Collins Avionics, and I think it's good, very good. So the outputs of each function are transformed into the functional requirements of this function. Here we can use templates, boilerplates, to describe each requirement. Also, we represent non-functional requirements. Non-functional requirements, also we use templates. A very important issue is not only represent the requirement textually, but also represent the rationale of each requirement. It's a very good best practice with each requirement to have its rationale. Here we have requirements related to maintainability. After we identify the physical architecture, here we have the main subsystems: avionics, electrical, mechanical, propulsion, and mission. For each subsystem, we represent the types that it contains and the parts. Here is the type, here is the part. With this definition of the electrical subsystem using a block definition diagram of SysML, we can represent the internal block diagram. But before, it's important to know the functional allocation. So we represent the functional flow represented earlier, but allocating the function to the part that will perform the function. So we use swim lanes to allocate the function to the part. And after, we represent using an internal block diagram the parts. We represent the parts, the connectors, and the ports. In this case, we are using SysML 1.1. So we are representing flow ports and standard ports. Here we have flow port for power, and we have here a standard port for commands. Currently, we are using flow ports and proxy ports. That is version 1.3 of SysML. Currently, in another project for a medical device, we are using flow ports for power, energy, mass, and we are using proxy ports for these kind of things. It's very important to identify the heuristics we applied. Here we apply heuristics related with maintenance, maintainability requirements. We use heuristics related with safety, and we use general heuristics for modularity. Group and allocate functions that are strongly related to each other, separate functions that are unrelated. This is an heuristic for create a modular architecture. Choose a configuration with minimal communications between the subsystems. This is minimal coupling. So it's very important to identify the heuristics we are using. Some of the heuristics related with maintainability are from several sources, and one book, very well-known book about maintainability that is referenced in our book. And in the safety, we use diverse heuristics. Each part is also described with a template describing the input, the output, and the functions it allocates. To conclude, I think the important issue in a methodology is how to think. It's very important to teach the users to think in abstract, to identify abstract functions, to identify abstract objects, abstract components that is very difficult for people. Currently, my students, for example, they are very good identifying physical objects, but identifying objects related with events, related with transactions, related with behavior, they were not as good. So we have to identify to have some methods, so best practices to help them. I think we can help also systems engineers to apply SysML and to apply this best practice related with model base. And also we have to teach the specialty engineers, electrical engineers, software engineers, mechanical engineers, to understand the models created by the systems engineers. So methodology is a way to promote and help people in all these issues. Thank you very much. If you have some questions, I am open to answer them. Thank you very much.
Thank you, Jose. That was really good. Enjoyed that. Do we have any questions? No? Okay, well, I will be making the video available. I'll email everybody through Encosi with that. I will speak to Jose about whether or not he's prepared to share his slides with us as well.
Yes, yes, I will send to you on the slides. Yes.
Brilliant. Thank you very much. And I guess we can also pass on any questions that you might have if you think of any. And obviously, I'll also include the link to the book, which is available on Amazon and other good bookstores.
Yes. Also, the book is in some libraries. For example, in Cranfield University, Oxford University libraries have right now the book.
Okay, that's cool. So if that's it from everybody, if there's no questions, then I'll just take this opportunity to thank Jose again for his time.
You are welcome.
And also just to point out that we would like to do some more of these. So if anybody has any suggestions, if anybody wishes to present anything, or they'd like to nominate somebody that they'd like me to ask to present, then please do get in touch. But apart from that, thank you very much for your time, and I hope it was really useful. I know it was for me. Thank you.
Thank you very much.
Thank you.
Thank you very much. Bye-bye.
Bye.